Am I coming through now? Oh, there I am. Okay, so polar equations of conics. To start this off, we're going to go back to where we kind of started this whole conic section stuff, talking about parabolas and this whole focus directrix definition of a parabola. Well, that focus directrix idea works for all conic sections. We just don't really talk about directrices when it comes to ellipses and hyperbolas because we don't really need to be able to write those equations the other way. You just need to think about where are the foci and where are the vertices and where's the center and all of that kind of stuff, and we were able to come up with those. But if we want to write them as a polar equation, then we have to bring that back. Okay, so let's say this is a curve that is a part of a conic section. Might be a parabola. It might be an ellipse. It might come back around and actually finish off the ellipse. It might be part of a hyperbola. Maybe there's another curve over here somewhere. In any event, it's a part of a conic. Okay? And there's this kind of imaginary line. Oh, that doesn't really look perpendicular. This is supposed to be perpendicular, though. So you've got a focus, you've got a vertex, and then your directrix right here. All right. And this dotted line, this is called the focal axis. I think we mentioned that briefly before, but never really did anything with it. Just kind of knew, oh yeah, that's where the focus sits. Okay, so we're going to use this kind of setup for any conic to describe some stuff. And we have to use eccentricity to do it. Okay. Now there's another way of looking at eccentricity. It ends up coming out to be the same fraction as the way you calculated it before. I believe before we did C divided by A, right, was the eccentricity of a conic. You guys remember that little formula? Okay. If we pick some point on the conic, call it P, and then we measure the distance from F to P, and then measure the distance from P to the directrix, so we'll call this point D, and this should be perpendicular then. The eccentricity is also equal to the ratio of those two lengths. Okay, so eccentricity is defined as PF over PD. Okay, now let's talk about the parabola case for just a second, because this should make a bit of sense. What was true about a parabola of any point on the parabola in terms of the focus and the directrix? Equidistant, right? What's the eccentricity of a parabola? 1, right? Does that make sense? That if I define eccentricity this way, still holds true for a parabola for sure, right? Okay? So that ratio works for that too then. And then same way that we talked about before, if the eccentricity happens to be larger than 1, so if PF is a longer distance than PD, then it's a hyperbola. And the flip-flop is true. If the PF is shorter than PD, then we've got an ellipse. Okay, that's how the directrix comes into play with those guys as well. Okay, but we're going to use this idea to help us derive the formula for this. But I think it's probably good to just remind ourselves about these little eccentricities again of what does what, because that's going to definitely play a role in what we're doing later on. All right, so E equals 1's a parabola, greater than 1 hyperbola, less than 1 ellipse. Later on, you're going to have an equation of a conic in polar. And the E is going to be part of that equation. And so what I might ask you to do then is to look at the equation and tell me what kind of conic section is this an equation for. And if you can identify where the E is in the formula and what the size of it is, you can use this idea to help you determine what you got before you even graph it. Okay. So, all right. So, how do you use this idea? All right. Well, I'm going to take this picture here. I'm going to just kind of twist it so it's easier to look at, and I'm going to redo it a little bit and put this thing, like I said, with the focus on the origin. That's the only way this stuff works, if we put that right on the origin. So here's where your equation comes from. Now in the polar world, we don't call the origin the origin. It's called the pole. Really? It's called the pole. That's why, like on the planet, you have the North Pole and the South Pole, because everything revolves around those, right? So it's a pole. Well, think about it. It's called a pole because you could think of it as a physical pole that things rotate around, right? At least with the North Pole and the South Pole with the Earth, right? Well, in the polar world, okay, things revolve around a point, okay, in 2 dimensions. But if this was in 3 dimensions, you could think of a pole like poking into your paper, and everything is rotating around that point, okay? So the origin kind of serves like a pole then. Okay, so we say the focus is at the pole. So I'm going to write that down here. Sure. Then you'll get to laugh and they won't know what you're talking about. All right, so we'll make the conic kind of come around this way. And again, this could continue and form an ellipse. It could make a hyperbola. It could make just keep going and be a parabola. Doesn't matter. And then our directrix is here somewhere. And here is that vertex. So we'll put our point P again on there, point D, and those segments that we would then measure with our eccentricity, right? And because we're in polar, whenever we measure angles in polar, everything comes off of the positive x-axis, right? Which is right here. So here's theta. Okay, so the angle of rotation, we're thinking of this little segment FP, that's theta, what we rotate up to get to there. And from F to P, think of that as, remember we're doing polar coordinates, that would be then the radius. When we were plotting points in polar, we had everything based on how far did you rotate, and then how far apart, how far from the origin or how far from the pole is that point. So do you see if I out theta and r, I've created polar coordinates for this point P. Okay, so any point P that is on the graph of this thing has theta and r defined like that then. Okay, so if we can do this generically, we can figure out what is the equation for any point P that happens to be on it, and we'll have an equation for the whole schmack. So that's what we're trying to do here. Schmack. The whole thing. It's an expression. Just get over it. So think of a little right triangle here. So what is the length right here of the bottom of that triangle then, if I'm using r and theta? Think back to your polar equations and your vectors and that sort of thing. In terms of r and theta, how would I figure that out, how long that is? I'll give you a hint. It has something to do with cosine or sine. So it's cosine because it's in the x direction. R cosine, right. Okay, so this distance here is r cosine. Okay? And if you remember our whole talk about directrices with parabolas, we used the letter K to determine how far the directrix was. So like we would use, like, this would be the equation of the directrix would be like x equals k. So this distance from here to the directrix is k. That's the variable we used before. So in the picture, what do I have as far as the length of PF? What did I use to measure the length of PF? R. Okay, so that's equal to R. Here's the trickier one. What's PD? You got it. You just do a little subtraction, right? It's the K minus that little R cosine. Oh, that should be R cosine theta. Sorry, missed that. Yeah, it should make more sense now. So PD is K minus R cosine of theta. Okay? So, density we said was equal to PF over PD. So we're doing a little substituting here. The eccentricity is equal to R divided by K minus R cosine theta. But whenever I put something into polar, I want to solve it for R, right? Yeah. So I got to figure out a way to solve this equation for R. Any ideas? Yeah? Certainly a good start. So E times K minus R cosine theta equals, okay, now I know that's equal to R. It's not technically solved for R just yet, right? Because there's still another R over here. So, ideas? Okay. All right, so I got that distributed. That's good. What should I do now? By itself. Two of them in there. So add that term to the other side so we can put the r's on the same side, even though it's got that other stuff with it. So EK equals R plus ER cosine theta. Okay, we're closer. What now? Oh, you're close. Take out the R. Factor, right? That'll leave just one R instead of two then. And then we can actually finish this thing up. So EK equals R times 1 plus E cosine theta. And then you do a little dividing, and you got it. Yeah, maybe a little bit. And that's it, folks. So, look at that equation. What things do I need to know about my conic section before I can write it in polar form? I need to know its eccentricity, for sure. What else do I need to know? The K. Where's the directrix, essentially, then, right? Because that's what K tells us. So if I can figure out where is the directrix and what is the eccentricity, I got it, okay? Yeah. Now, here's the thing. This is the equation for every conic section that opens left around the focus, because that's how I oriented it to start with. Do you guys see how if I had made it like an opening up parabola, I'd be using sine instead of cosine, and there's some negatives and things that might switch and all of that. So let me quick lay it out for you. We won't have to do this 3 more times, I promise, because there are 4 orientations technically, because we're not rotating axes on these, because that would be really bad. So it's just, it either opens left, right, up, down, and that's it, okay? So
wouldn't it be easier to rotate axes a lot?
if I were to take the entire, we might be able to do that, but not right now. Just not right now.
Yeah, it would be. Yeah. You just add to and subtract from theta.
Well, okay, so the theta, all this theta is serving as is what is the angle that you want to go to find a point on the existing parabola. So to take the entire graph and turn it would not be the same thing as changing the number of theta, because theta is still just theta in the equation.
But if you add theta, like if it's r equals ek all over 1 plus e cosine theta plus 90, or theta plus pi.
I hear what you're saying. So you do some kind of a plus or minus something to the theta as an, you might have something there.
Just like adding.
We can try.
Subtracting 2x in a regular rectangular.
No, I hear you. Yeah, we could do something like that. Maybe try it out and see what happens.
It'd actually be really easy.
I'm going to just lay out all the different orientations and how the equation changes for you, just so we don't have to derive it 3 more times. So here's the one we already did. And I'm going to get a little bit more technical here. It's r of theta. Yeah. So ek over 1 plus e cosine theta. That's the one we just did. Right, so now if the conic goes around the pole to the right, how is this equation going to change? It's going to be a minus cosine instead of a plus cosine. That's it. Otherwise, it's the same. All right, and then the up and down. So if it opens down, how is that's going to change?
1 minus psi.
Yeah, it's going to be plus sign. Yeah, it's plus. Because notice how when it opened to the left, it was plus. When it opened to the right, it was minus. So it's kind of the opposite sign of what you would expect then. So ek, this would be 1 plus e sine theta. And then if it opens up, ek over 1 minus e sine theta. Okay, now these are not ones that I'm going to give to you. I'm going to expect you guys to know these. But the thing is, if you know the one, it's very easy to adjust it to get to what you need depending on the orientation of it, okay? Cosine, like with pretty much everything we've looked at, deals with things that go in the x direction, right? So these that open left or right are cosine. Sine always talks about the y-axis, so ones that open up or down involve sine. And then it's just that little plus or minus sign. And it's just the opposite of what you would expect. So if it opens right, it's minus. Left is plus. Up is minus. Down is plus. So that sort of thing.
Because like when you're measuring, it's like the opposite quadrant.
Yeah, exactly. So, yeah, and it deals with where the directrix is really. I mean, look at this one that we did right here. It opens to the left, but the directrix was positive, and we were using that positive number in our calculations to do it. So, yeah, it would be a negative k if it was over there, and that would flip it. That's why it changes. So, yeah, all right. So, let's take a look here then at doing some of these things. We'll just start with some simple ones where I give you an eccentricity and a directrix. And then later on, we'll look at ones where maybe we don't have all the information we quite need. We need to modify some things a little bit to get it to where we want it. And then we'll graph a few of these on our calculators, too, to take a look. Bless you. Okay, so this one. Write a polar equation of a parabola with directrix y equals -5. With all of these, I don't know if they're going to put it in every question, but technically focus at the pole. I guess if I'm going to be precise, I need to put that on there too. But, so we said before, we need to know E and we need to know K. But we also technically need to know its orientation, though, right? Because that affects how the equation works, too. So what do we got here as far as orientation is concerned? Which way is this thing opening? Try again. Right? If the directrix is down at y equals -5, it's got to open up away from that, so it's opening up. Okay, so we got one that does one of these. So we also need to know the E and the K, like we said. So what's the K? Don't need to worry about the positive or negative. K is always positive. The equation takes care of the fact that it was positive or negative. And what is the eccentricity? 1. It's a parabola, right? So I don't even need to tell you the eccentricity for this one, because if you know it's a parabola, you know the value of that. Okay? So since this thing opens, we're going to be using the equation r of theta equals ek over what then? The e sine theta, right? Yeah, 1 minus e sine theta. Okay, so then let's take our k and our e, put them in, we'll be done. Where did we get the e? Yeah. It's a parabola. Parabolas are always 1. So I was a little sneaky there, yeah. So r theta e times k, so that's 5 on top. And then 1 minus sine theta. All right. So like I said, let's take a look. Let's go on our calculators, put them back into polar mode, and let's graph this thing. So maybe you need to share then. Everything's in radians with these. So when you've got your mode screen up, you should see this. Should be in polar, should be in radians before we do anything else. And then into our y equals, so r was equal to 5 divided by 1 minus sine theta, like that. And if when you graph it, you're not seeing what you think you should see, it should be a parabola just opening up around the origin, you might have to play around with your window a little bit. Mine, I got 0 to 2 pi. That should be pretty good. Maybe my theta step 0.1. The x min and max, you don't need to get real big on this one, I don't think. Maybe just go -5 to 5 either way. And that should be enough. Let's take a look at this guy here now. All right, yeah, so there it is. There's your parabola wrapping around the focus. I'm going to make my x scale just a little bigger, though, just so that's a little easier to see. Maybe these go -10 to 10, and let's see if that helps. Nope. On a parabola, yes. Because that's the way a parabola works, is that, remember the distance, well, I guess this is probably an easier one to look at. this distance here and this distance here are always the same because the eccentricity is 1 for a parabola. But for other ones, it could be bigger or smaller than 1. So if it was a hyperbola or an ellipse, that could be a little bit closer or further away from the directrix then. So, question, sir? Yeah, sure. I've got 0 to 2 pi for my min and max. And my theta step is 0.1. And then I went negative 10 to 10 on the x and negative 5 to 5 on the y. And then that should get you what I had there. All right, so graphing and taking a look at them before we move on. Okay, let's try another one. We'll make this one not a parabola so we can see a different type of conic on our calculators here. So how about, oh, if I can get some lead out of my pencil here, maybe. There we go. So let's write the polar equation of a conic with E equal to 3/5 and a directrix at x equals 3, and then, as always, focus at the pole. So the eccentricity is 3/5, directrix is x equals 3. What kind of conic do we have here? Ellipse. So when we get this equation and we go to graph it, we should be looking at an ellipse, right? So, all right, let's see if we can do that real quick here then. So, orientation, which way are we going? Opens to the left. Yeah, because the directrix would be here somewhere, and so it's going to have to wrap around this way. Focus at the pole. All right, so let's think about use of K and E, and then what equation we need to use and dump them in. So, what's K? K is 3. What's E? 3/5. So, the equation we need to use, which one is it going to be then? 1 plus cosine theta. Yep. Cosine. Yeah. Alrighty, so let's put them in there. We might do a little bit of simplifying on this one too. We got 3/5 times 3 over 1 plus 3/5 cosine theta. Now there is a way to eliminate fractions out of these things, because the fractions are going to pop up frequently. Well, yeah, so they both the numerator and the denominator have a 3/5 in there, right? Both those two little fractions have a denominator of 5. So to cancel all of that out, if I multiply the entire big fraction by 5 over 5, I just got to be careful in the denominator that I distribute it, though, to everything. But that'll take care of it. So what I'm going to end up with here then, whoops. Let's see if you can find one here. It's going to be, in the numerator then, it should be just 9. And the denominator is going to be 5 plus 3 cosine theta. Everybody follow what I did there with my algebra? 5 canceled the 5, leaving a 3 times 3, it's 9. And then I distributed underneath to cancel the 5, but then 1 times 5 is 5. So, yeah, we end up with this. So, all right, so go back to your calculators. Punch that one in. See if you see the ellipse. You might have to zoom out a little bit to see it, but we should have a nice little ellipse opening to the left around the origin. All right, so I got, keeping the window the same, I got that. So it kind of looks like a circle, but remember, our window isn't exactly square at this point. If you zoom square it. Uh-huh. So, yeah, a little better. So it's not quite, you know, a real nice looking ellipse. It's a little bit circular, but that's just because its eccentricity is fairly small, and so it looks more circular. But and truth be told, when I put it up on the projector like that, it stretches it vertically a little bit, so it makes this one look more circular than maybe it does on your calculator. I don't know. Yeah, that's an ellipse, and one focus is at the origin. So if you can kind of visualize that. You've got one focus right there where the x and y axes come together. There is another focus on here, okay? And we could pinpoint it if we wanted to, and we'll do a bit of that tomorrow, actually. We'll take a look at these polar graphs on our calculators and kind of play around with them a little bit. But if we were to kind of estimate here, do you see how the focus is at 0, and then this vertex looks like it's about at 1, right? So we know that this has a distance of 1 from here to here. Well, we could kind of guess at about how far over this thing goes. It's 1, 2, 3, 4, 5.5. So if I go 1 in from this side, that's where the other focus is, right? So it's like negative, well, it'll be at like negative 3.5. Does that make sense? So we kind of use the symmetry of this thing. We could kind of make a guess at where that other focus is. It's somewhere about negative 3.5 on that x-axis there. And also, using that, we could make an estimate to be about where the center of this thing is as well. And then what we can do is, once we have that, we have enough information where we could then take it back into rectangular. So we can have our polar equation of this thing and pull it back into a rectangular equation. If I know where the center is, if I know where the foci are, if I know where the vertices are, that's enough information to get back into that regular ellipse equation we worked with before that was with the x and y. Yeah. Using the eccentricity? Well, the eccentricity is a ratio of two measurements, though, so it's not a direct measurement of anything on there. But you could. You would have to know where this, because it's in the old way of doing it, it's C over A, right? So if you knew, you'd have to know exactly where the center was, though, because the measures of C and A come off the center of the ellipse, right? So technically, you'd have that information first and be able to track how the center is the focus and the other.
How far away the right focus is from the vertex.
If you knew that, and that's all you knew,
then you could work it out how far it is, how far away it is from the other vertex.
You'd have to know the other vertex too, though. So yeah, so because the eccentricity is a ratio, you always need something else with it to actually get a measurement. Something else. So what we're going to do, though, is you can trace these things in polar still. So we'll trace it, and we'll be able to figure out exactly where these two vertices are by tracing it. Okay? By plugging in a theta, we can put it to one of those vertices exactly, and then use the value that the calculator gives us to figure how far away are we, measurements to figure out what that rectangular equation was that it came from. Okay? We'll worry about that tomorrow. That's a little beyond what we're doing right now. But yeah, anyway. I want you guys to do today, and then I think we can be good, is if I give you a polar equation, can you work it backwards and tell me what the eccentricity is and what the directrix is and where the directrix is and all that. Okay, so we can definitely go this direction with it. That's not too bad, but can undo it as well. So let's say we got something like that. So describe the graph of r of theta equals 2 over 4 plus 7 sine theta. So by describe the graph, I mean, what kind is it? Is it an ellipse, hyperbola, parabola? And then, yeah, hold that thought. Yeah, get there in just a second. So anyway, so what kind of graph is it, or what kind of conic section is it? What's the orientation of it? Where is the directrix? All that kind of stuff. Okay, and yeah, so Tiffany gave us our first step here. You can't have a 4 here, right? To know what the eccentricity is anyway, right? Because this is still a valid way, because we did it in the last one. You can have a different number there and graph it, and it is a polar equation of that. Work it back to look something like this, right? And so this has to be a 1. So if there's anything else there, then we're going to, bless you, we're going to have to be doing a little bit of factoring and that sort of thing to pull numbers out, okay? So let's start with that. So if I take a 4 out of 7, what's left? Don't overthink it. It's actually easier than you might think. It's not 4 7s. 7 fourths. Right. So we're not quite looking the way we want yet. That 4 needs to go away. What can I do with it? Well, if you want to think of it that way, yeah, you could multiply by a quarter over a quarter, and then what would you have on top? 1/2. Or think of just taking this 4 and bringing it up with the 2 as a denominator. That's kind of how I do it in my head. But the quarter over a quarter thing is totally valid. That works. Either way, you're going to end up with 1/2 on the top over 1 plus 7 fourths sine theta. Mm-hmm. Mm-hmm. Yep, exactly. So, yeah, the eccentricity is 7 over 4. So what kind of conic do we have? Hyperbola, right? Okay, and like Tiffany just said too, then the 1/2 we know is equal to EK. The E, so we could figure out the K, right? So 1/2 is equal to 7 fourths times K. So K would be equal to what? 4 over 14, which reduces, so 2/7. Yep. So, once we got the K, we got the E, we know it's a hyperbola, can look at the equation and get the orientation. Just sketch a little graph of this thing. So, which way does this thing open around that focus? So it goes, yeah, plus sign, so it's going to go down. Now, figure out precisely where, like, this vertex is or anything like that. But I do know that the directrix is 2/7, so it's going to be a pretty tiny number, whatever it is. But that directrix is going to be up here at y equals 2/7. And since this is a hyperbola, again, I can't pinpoint the other piece of it anyway, exactly where it is. But I do know that there is supposed to be somewhere another half of it over here, right? If this thing is indeed a hyperbola, and there would be another focus up here somewhere as well. Okay? Things on our calculators tomorrow, we're going to investigate some of that as well. Like we talked about the ellipse, where is that other focus? How do I know where that other part of that hyperbola actually is? Well, by doing a little bit of tracing these things, we can find it on the graph what that is. Without a calculator, I know kind of thing is supposed to look like, though. Okay, what's the orientation of it? What kind of conic is it? Where the directrix is, all of that kind of stuff. I can get that down and draw a pretty decent sketch of the thing, like I just did, without too much detail. Okay, so we're going to stop there for today. Like I said, tomorrow's going to be our big calculator day with this stuff, doing some investigating that way. And you'll, yeah, I know, right? And no assignment, it'll be tomorrow. All right, so you're free. Look at how to conic on your calculator. Okay, so we're ready to roll here, guys. I want to quickly review what we were doing yesterday, just so we're all back up to speed here a little bit. So the beginning, we just derived the equation of a polar conic, and then we went into doing some analysis of these. So both directions, like if I give you information about a conic section, can you then write down the equation of it? And if you have the equation, can you then analyze that and tell me something about what kind of conic you have, where's the directrix, what's the orientation, stuff like that. So this first one we did, I said it was a parabola, directrix was y equals -5, so we knew it was a parabola that opened up around the focus, which would make it an ek over 1 minus e sine theta equation. So we could find the k and the e from the information, plug it in, easy, done. Next one, I gave you an eccentricity, gave you a directrix. In this case, because the eccentricity was less than 1, we knew that it was going to be an ellipse. X equals 3, directrix let us know that it was going to open to the left around the focus. And so we were able to plug the numbers in, do a little bit of simplifying, and we got our final equation, 9 over 5 plus 3 cosine theta. And then the last one I just said describe the graph. And so we had to analyze that equation, pull the information out of it, had to do a little factoring to get at the eccentricity then, because remember this first number is supposed to be a 1, and then the coefficient in front of the sign is the eccentricity. So if we pulled out a 4, that gave us 7/4, which means we had a hyperbola, and then that 2 on the top became a 1/2, and that's going to be equal to e times k. So if we plug in the eccentricity that we know, solve it for k, we get 2/7, so we can approximately place that directrix in there, so we can kind of draw a decent sketch of our hyperbola. So today, we're going to take a look at the equation of a conic. We're going to see if we can work this thing back so that we can figure out what is the Cartesian equation from whence it came. Okay? So, and we'll use our calculators to help us with that. And then there's also another alternate polar equation that only works for ellipses that I'll show you. And that'll help us get some other information about those as well that we could use to analyze it a little bit further. Yeah. There will be the homework today. Yep. So, all right. So let's give this a try. So let's say the conic section that we're interested in. So R equals 3.2 over 1 minus 0.6. And this was a cosine? Yeah, cosine theta. Okay, and so for this one, analyze the conic section, and then we also want to include values of A, B, C, and E. Which means we're going to have to pull it back into a Cartesian equation, so an equation involving x and y, to get us the A and the B and that sort of thing. So, all right, so let's give this thing a try. So what is the eccentricity? Let's start with that, because that we can get right from the equation. 0.6, okay. So, seriously. I'm having some issues with this lead. All right. Okay, so next what I'd like you to do is, to be able to analyze for the A, B, and C, let's graph this thing on your calculator real quick. Take a look at it, okay? Should be seeing an ellipse. And again, make sure your calculator is in point mode and in radian mode, if it is not already. And if you make your x min and max -5 and 5 and your y min and max -5 and 5, that's going to give you a pretty decent look at this thing. So I'm getting something like that. No? I don't know. See my equation. Did I screw something up? That's not right. Never mind. Let me try again. Oh, yeah, it's a little bigger. Okay, hold on. So my x needs to be a little larger. There we go. Okay, so you can look at this and probably make a decent guess at where these vertices are, right? On the ends there, on that major axis. Now, I want to know for sure, though, okay? So I can trace this thing, or I can value on there somewhere. But remember, when I do that, the x that you would normally plug in the past is now theta. You plug in a theta and it gives you an r. So let's try that once. So if I second calc value, it wants me to give it an angle. Now, if I'm going to be getting endpoints here, what do you suppose is going to be my theta? Possibly like 0 or 90 or 180 or something like that. But again, we're in radians, though. So maybe I try like let's do a pi over 2 and just see where it puts us. Okay, so like a 90-degree angle, where on the ellipse would that be? That one's right there up on the top. So maybe if I do it 0, that'll put me all the way on the right. Let's try 0. There it is. Okay, it's on the far end there.
Why does pi over 2 give you the x intercept, or the y intercept? Didn't it give you the top of the point?
Because as you sweep from 0 to 90, it gives you varying radii through here.
Yeah, but
90
should still be 90.
It is. You're starting from here.
Oh, origin. Yeah.
So it's like tracing it to there. It's giving you different radii as you go around to there. So 0, and the nice thing about this is, too, notice how it gives you both the x and the y. That's pretty sweet, right? So if you have a theta of 0, we're at the point 8, 0 there, okay? So why don't we quit? Let's draw a sketch of this thing. We'll start labeling some of these points that we can use. Because we've got one of them that's going to be very helpful here. That looks really bad. Okay. This point here we just found was 8, 0. Here's a focus. All right, if we need to figure out where this one is, what should I plug in? We do pi. We should be over there, right? Okay, so let's do second calc value. Let's put in a pi. Yeah, and there we are. It's on the other side there. So it's at -2, looks like, right? -2, 0 is that other point. All right, so we can put that on here then. All right, and that should be all we really need our calculator for here. Okay, so where is the center of this ellipse then? At 2, 0? Nope. 3, 0, yeah. You guys all see that, right? Because it's exactly halfway. It's 5 either way from 3. Okay. And so knowing where the center is, we can at least find A and C, right? So what's the value of A then? Should be 5, right? From the center to a vertex, either way is 5. Okay. What's C? Yeah.
Wait, I have a question. When you
Sure.
go like the -2, 0,
Yeah.
when you go like second calc value, what do you plug in for the theta?
I did pi. Because pi would be that side of the circle. Like you think unit circle?
Yeah.
Zero's over here, pi's over there. So we did a 0 and a pi and got the ends. Okay, so what's our C? 3. Because remember, the focus is at the origin, right? So from a focus to the center of the ellipse, that's a distance of 3. So C is 3. We still got to figure out B. Now, how do I figure out B? Yeah, it's an ellipse, right? B squared plus C squared equals A squared, so I can use that to find the B. So B should be 4, looks like. On that one then. Did I do my math right there? I think so. Okay, so I'll take this a step further then. Can you then write the Cartesian equation for this thing? What would it be? So we've got, this is, yep, x minus 3, good, squared, over 25. The A under the x because the x-axis is the major axis, right? Okay, so x minus 3 squared over 25 plus what? That's it. Yep. So we had to use our calculator to kind of assist a little bit there, but we were able to take a polar equation of a conic and effectively bring it back to its Cartesian equation that is the same. Okay. C, the focus is always at the origin, and the value of C is always this distance from the center to a focus then. Okay. What if the center what?
Where the focus be, like the center was, I guess
Oh, if the center of the ellipse was actually on the origin, then we wouldn't have this graphed polar the right way. All of these are going to be off-center a little bit because those equations that we're using to make these in polar assumes that a focus is on the origin at all times. So if you were to not have that, then the original equation we would have used wouldn't have worked. So, okay. That's doing that stuff. So this alternate equation. Now your book, again, does kind of a nice little job of showing you where this comes from and all that. And if you'd like to look on page 680 at the bottom of the page, do a nice little proof. Yeah, to save time. All right, now this one is convenient because it involves A and E in the same equation. So we get equals A times 1 minus E squared over 1 plus E cosine theta. Now, orientation could change the bottom of it just like before. Okay, so for this particular one then, this is an ellipse. Focus at the origin that comes around like that. Right? Because the plus cosine, it should open to the left around the focus. If it was a minus cosine, it would open to the right around the focus. If it was a plus sign, it would open down. Minus sign opens up. So just kind of keep that straight in your head too. It's not always the plus cosine, but in general, it's just that numerator that's kind of the new deal this time, right? Only works for the ellipses, but it's A times 1 minus E squared. So what that then is we can take the equation of an ellipse, analyze it without having to do our calculator and figure out the A that way, because it's embedded as part of the equation then, okay? So do an example of that real quick here. So let's say we've got R equals, I don't know, how about negative let's say that is our equation. Oh, I can't do that. Shoot. Hold on. Try again. That's not an ellipse. Let's try that. Negative 18, yeah. So let's analyze this one then. And so we know the eccentricity of this thing is 1/2. Oh, shoot. Okay. I shouldn't do this from off the cuff. Make it positive 18. It's not going to work if it's negative. Sorry. All right, so I got one that works. All right, eccentricity is 1/2. So we have verified that, yes, it is an ellipse, right? Which means we're allowed to use that equation that I gave you up there. Okay? So this 18 is equal to A times 1 minus E squared. Because I already know the eccentricity, I know means to find A, right? Plug the 1/2 in. And we're going to solve that for A. So 18 equals A times, that would be 1 minus 1/4, so that's 3/4. And if I multiply 18 by 4/3, oops, 24. Okay, so I got A is 24.
Why did you multiply by 4/3?
divide by 3/4, multiply by 4/3. Good. Yeah. So I now have my A, which I could then use to figure out what this thing looks like. This is an ellipse where the focus is at the origin, and because of the plus sign, it opens around this way. All right. Now remember when we talked about electricity, we said that it was C over A, right? Well, now that I know E and I know A, and if I know C, I can start pinpointing things on this graph that I just drew. Okay, so let's do that real quick. So E equals C over A. All right, well, 1/2 equals C over 24. So what's my C then? Be 12. Okay. At the origin, we know it has to go this way because of the plus cosine. Where's the center then? Be at negative 12, right? Okay. Negative 12, 0. So where are my vertices then? You're close. Was right. And negative 36. Remember, A always comes off the center of the ellipse, right? So it'd be all the way down to negative 36 then. All right. So now I've got my A, I've got my C. I could find my B, an equation for this thing if I wanted to. We've already done that work, so I'm not going to repeat all of that stuff. But you get the idea, okay? Didn't need a calculator to do any of it, right? Because I have this alternate one. It only works for ellipses. Hyperbolas, parabolas, you're kind of stuck. But I get back all the way if I were of a mind on this one to do that. Okay? So it allows me to pinpoint things that I need to figure out the equation of this thing. Okay? So I think that is about it. The only thing maybe I should at least mention is there are some homework where they're going to give you 2 polar points on the graph, and you have to use that to determine what you have. And it has, some of them are a hyperbola, some of them are an ellipse. So, like, for example, 21, I think this is on your assignment. Question number 21, they give you 2 points, 1.5 and 6 pi. And it says equation for the ellipse with a coordinates your axis. Okay, these are polar points, r, theta. Okay, think about what we were doing in our calculator. Well, I was draw a picture. So 0 is over here, pi is over there. So if I'm at an angle of 0 and my radius is 1.5, I'm out here at 1.5, right? This one, my radius is 6 when my angle is pi. The angle of pi takes me all the way over to here, and then I'm coming out 6 from there. So I'm out to here. Not to scale. So my ellipse would be doing like this. Okay. Do you see how the information I need now, though, to come up with an equation? Just like we did after we found that information on the calculator, right? It's just taking it the same, doing the same stuff with it after you have those 2 points there. Okay? So don't get confused by these polar points, that's all they want you to do with that. So you can kind of take it from there and do it the rest of the way. So you guys get started on your homework here then. We got a decent amount of time, so hopefully we can get a decent chunk taken care of.